Good day, my dear learners. This is Ms. Jen, your teacher in basic calculus. Today we shall focus on the limits of transcendental functions. Specifically, at the end of this video, I hope you would be able to compute the limits of exponential, logarithmic, and trigonometric functions using table of values and graphs of functions, and illustrate limits involving the expressions sine t over t, 1 minus cosine t all over t, and e raised to the t power minus 1 all over t using table of values. Let us first define what a transcendental function is. According to Britannica.com, transcendental function is a function not expressible as a finite combination of the algebraic operations of addition, subtraction, multiplication, division, raising to a power, and extracting a root. Examples include the functions of the logarithm of x, sine x, cosine x, e raised to the x power, and any functions containing them. Such functions are expressible in algebraic terms only as an infinite series. In general, the term transcendental functions means non-algebraic. Transcendental functions has many real-life applications, one of which is the problem that you see on the screen. When the lockdown has been implemented, a family has received 20 kilos of rice as relief. In order that it will last for some days, the mother thought of a strategy. Every day, she will just use 1/10 of the rice that they have received. Just in case the cooked rice will not suffice to feed everyone, she will just mix it with corn or sweet potato. Will there be a time when they will have no rice to cook? To be able to solve this problem, let us illustrate using a table of values. Now take note that the mother will cook 1/10 of the rice they have received every day. So let's start with day 0. So day 0, they will have 20 kilos. Now after the first day, the mother has cooked 1/10 of 20, that is 2 kilos. Then subtract that from 20, so the number of kilos of rice left would be 18. Now doing the same procedure, getting 1/10 of 18, then subtract that from 18, we will have 16.2. The same with the third and the fourth day. Probably you might be wondering, how did I get the number of kilos of rice left on the 25th day, on the 100th day, on the 200th day, when I do not know the number of kilos of rice left a day prior to the 25th day or prior to 100th day or 200th day. Now take note that this situation can be modeled using an exponential function of the form y equals a times b raised to the x power, where a is the constant, b is the rate of change, and x is the independent variable. Now in this particular situation, let's identify the given. The constant is 20, whereas the rate of change is 9/10. Now, since we are after to the number of kilos rice left, how did we get 9/10? That is 1 minus 1/10, the number of kilos of rice left being cooked every day. So that will give us 9/10. Okay, so 1 whole minus the number of kilos of rice being cooked will be equal to the number of kilos of rice left after cooking. Okay, and then we have x as the day number. So for example, day 1, day 2, day 3, and so on. So let's see if we will have this given, we would be able to form an equation that will represent, or a function that will represent the kilos of rice left. So y as the number of kilos of rice left equal to 20 times the quantity 9 over 10 raised to the x power. So what if we would like to get the number of kilos rice left on the 5th day? So we will have to solve for this. Y equals 20 times 9 over 10 raised to the 5th power. Now using our calculator, that will give us 11.8098, or approximately equal to 11.81 kilos of rice left. So we used that function, y equals 20 times 9 over 10 raised to x, in order to get the kilos of rice left on a particular day. Now going back to the main question, will there be a time when they will have no rice to cook? What's your answer? Probably you may be answering, yes, there will be a time that they will have no rice to cook. Or probably you will say no, because based on our table, there will always be rice left, even a small portion. So as you can see, on the 200th day, we still have a certain portion. So if you answered no, you are correct. Mathematically, there will be no time that the family have no rice to cook. However, if you said yes, you are also correct, because on a particular day, like we have 200th, on the 200th day, we will have the number of kilos rice left will be 0.000000001411. And take note, that is too small that it can be considered as nothing. So if you answered yes, you are correct. And if you answered no, you are also correct, depending upon your reasoning. Now, solving this problem, or answering the main question in the problem, will there be a time when they will have no rice to cook, is just like evaluating the limit of 20 times 9 over 10 raised to x as x approaches to positive infinity. So as you can see on the table of values that we have, it can be seen that as x approaches to positive infinity, the function gets closer and closer to 0. Looking at the graph, let's confirm if the limit of 20 times quantity 9 over 10 raised to x, as x approaches to positive infinity, is really equal to 0. So looking at the graph, if we will trace the graph as x approaches to positive infinity, or as x increases without bound, the value of the function gets closer and closer to 0. Take note that this graph is asymptotic to 0, so it really confirms our answer that the limit of 20 times 9 over 10 raised to the x power as x approaches to positive infinity is 0. Okay. Now let's have another exponential function. Find the limit of 3 raised to x as x approaches 2. Now in the previous lesson, you have learned that we can just evaluate the given function at f of a, or we can evaluate 3 raised to x at x equals 2. So if you are asked to get the limit of 3 raised to x as x approaches 2, we will just have 3 raised to the second power. Simplifying that will give us 9. Okay, so algebraically, we can evaluate the limit of 3 raised to x as x approaches 2 is equal to 9. Now, let's see if that will also be the same if we will have a table of values. Now, take a look at this table. Okay, we will evaluate first the function as x approaches to 2 from the left. Remember, in order to conclude that this limit exists, we have to prove or to show that the limit of the function as x approaches to 2 from the left is equal to the limit of the function as x approaches 2 from the right. So choosing a value at the left of 2, let's say we have these values. We have 0. If we will have x equals 0, then we will have 1. If we have 1, then f of x will be 3. Then until we have 1.999, then the function would have 8.990117919. Okay, so therefore we can just analyze the trend of the values. Now, as you can see, as the value of x approaches to 2, the value of f of x approaches to 9. So we can say that the limit of 3 raised to x as x approaches 2 is from the left is equal to 9. Now let's prove if we will have x approaches 2 from the right, we'll have the same answer. So using table of values, we choose a value from the right of 2. So examples of these numbers would be 3, 2.5, 2.001, and so on. Okay, so evaluating the function with this given value, we will have the corresponding value of f of x. Now, as you can see, as the value of x approaches 2, then we will have f of x approaching to 9. So in other words, the limit of 3 raised to x as x approaches 2 from the right is 9. Now, since these two limits are equal, we can conclude that the limit of 3 raised to x as x approaches 2 is 9. Okay, did you get that? Let's have another example. Or probably we can confirm using the graph. Okay, using the graph of 3 raised to x, we notice that, okay, the y-intercept is at 1. Now, the value at which x is approaching to is 2. So here is the point. Now, as you can see, this point has coordinates 2, 9. So we can see that as x approaches 2 from the left, we can have 9. Now, as x approaches 2 from the right, we also have 9. So therefore, it's really equal to 9. Okay? Now let us have example number 2. Find the limit of 5 raised to x as x approaches to positive infinity. Now as you can see, the value at which the variable x gets closer and closer to is not specific. It says that if x approaches to positive infinity, it means that the value of x is increasing without bound. So in this case, we cannot evaluate the given problem or expression using the idea of f of a. So we have to resort to tabular method or graphical method. So let's have the value as the value of x increases without bound. So we choose 0, 1, 2, 10, 25, and so on. We can have the value of f of x accordingly. So if x is equal to 0, we will have f of x equal to 1. And if we have 1, we will have 5. If we have 2, we have 25. If we have 10, f of x will have 9,765,625. And when we have x equals 25, we will have 2.980232239 times 10 raised to 17th power. So this means that this is a very, very big number. So if we will study the trend of the values of x and f of x, as the value of x increases without bound, the value of f of x also increases without bound. So in this case, we can say that the limit of 5 raised to x as x approaches to positive infinity is equal to positive infinity. Now let's confirm using the graph of 5 raised to x. Now we trace as x increases, so that means from left to right. As x increases without bound, take a look at what happens to the value of f of x. It increases also without bound. So it confirms our answer that the limit of the limit of 5 raised to x as x approaches to positive infinity is positive infinity. Now consider example number 3. Find the limit of 1/3 raised to x as x approaches to positive infinity. Now as you can see, just like the second example, we cannot use the idea of f of a in evaluating the given function. So we will use tabular method. So since we have x approaches to positive infinity, that means the value of x increases without bound. So let's say we choose these values, 0, 1, 2, 11, 20, then we would be able to get the corresponding values of f of x. That is just by replacing x here. So if x is 0, then we will write here instead of x, we will have 0, so that will give us 1. If x is 1, then we will just have 1/3, or in decimal form, we have this. And until we have 2, 11, or until we get the corresponding values for when x is equal to 2, 11, and 20. Now let's study the trend of the values of x and f of x. As the value of x increases without bound, we notice that the value of f of x is decreasing. However, it approaches to 0. So in this case, we can say that the limit of 1/3 raised to x as x approaches to positive infinity is 0. Now let's take a look at the graph of 1/3 raised to x in order to confirm our answer. That is really that this function, when evaluated at x approaches to positive infinity, will give us 0. So take a look at this graph. Now as we trace the graph as x increases without bound, we can see that we are approaching the x-axis. Okay, so the graph is asymptotic to 0, so we can really say that the limit of 1/3 raised to x as x approaches to positive infinity is really equal to 0. Now let me share with you some properties of the limit of exponential functions. So there will be two main conditions. There are two main conditions. If b is greater than 1, then we could have the limit of b raised to x as x approaches to positive infinity is positive infinity. Whereas if we have the limit of b raised to x as x approaches to negative infinity, we have 0. Now, if b is between 0 and 1, then we can have the limit of b raised to x as x approaches to positive infinity is 0, whereas the limit of b raised to x as x approaches to negative infinity is positive infinity. Okay, so what if we have the limit of a natural exponential function, wherein the base is the Euler number e, having an approximate value of 2.72. Okay, so in your calculator, just look for this symbol e in order to evaluate this given function. So again, x approaches to positive infinity, then we cannot evaluate this function by using f of a or evaluating the function at a. So we will use tabular method. Again, the value of x approaches to positive infinity. That means the values should be increasing without bound. Now take a look at the values of the function when we have this specific values. Let's study the trend. As the value of x increases without bound, the value of f of x also increases without bound. So therefore, the limit of e raised to x as x approaches to positive infinity is positive infinity. Now let's confirm using the graph. If we will trace the graph, okay, we have to select a value of x from here. Then as the value of x increases without bound, take note that the value of f of x also increases. That confirms our answer that the limit of e raised to x as x approaches to positive infinity is positive infinity. Now what if we have the limit of e raised to negative x as x approaches to negative infinity? Now, again, evaluating the function at x equals a will not give us a logical answer. So let's have a table. Now, since the value of x approaches to negative infinity, that means the value of x decreases without bound. So we choose from 0, then we have -1, -3, -30, -50, and so on. Then we have the corresponding values of f of x. Now take a look. As the value of x decreases without bound, the value of f of x increases without bound. So we can say that the limit of e raised to negative x as x approaches to negative infinity is equal to positive infinity. Now let's confirm using the graph of e raised to negative x. So as the value of x approaches to negative infinity, or in other words, as the value of x decreases without bound, okay, the value of f of x increases without bounds. That confirms our answer here that it's really equal to positive infinity. So here are the key points for the limit of natural exponential functions. So if we have the limit of e raised to x as x approaches to positive infinity, it's equal to positive infinity. Whereas if we have the limit of e raised to x as x approaches to negative infinity, we have 0. Then if we have the limit of e raised to negative x as x approaches to positive infinity, it's equal to 0. On the other hand, if we have the limit of e raised to negative x as x approaches to negative infinity, it's equal to positive infinity. Now what if we have an expression, or we have a function having e raised to x minus 1 all over x? Now if we will evaluate x at 0, we will see that we will be arriving at a form that is one of the indeterminate forms. So e raised to the 0 minus 1, we will have 1 minus 1 over 0. So simplifying that, we have 0 over 0. So this is an indeterminate form. Now before concluding that the function or the limit of the function does not exist, we have to confirm using tabular method. Now let's see if we will have the limit as x approaches to 0 from the left. So that means we have to choose negative numbers for x. So let's say we have negative 2, negative 1, negative 0.5, negative 0.09, and so on. And here on the second column are the values of f of x accordingly. Now study the values of x and f of x. As the value of x approaches to 0, the value of f of x gets closer and closer to 1. So we can say that the limit of e raised to x minus 1 all over x as x approaches to 0 from the left is equal to 1. Now let's see if we have the limit of the function as x approaches to 0 from the right. We choose values from the right of 0. Okay, so let's say we have 1, then until 0.000001, okay, until it gets closer to 0. And here are the values for the f of x. So let's study the trend. As the value of x approaches to 0, then the value of f of x gets closer and closer to 1. So we can say that the limit of e raised to x minus 1 all over x as x approaches to 0 from the right is 1. Now since these two are equal, then we can now confidently conclude that the limit of e raised to x minus 1 all over x as x approaches to 0 is equal to 1. So remember that If this expression e raised to x minus 1 all over x is involved in an expression, take note, this it's like multiplying the other components of the expression by 1. Okay, now let's confirm our answer with the graph of e raised to x minus 1 all over x. Here's the graph. Now we have x approaches to 0. So it says if we will have 0, here is the point where the abscissa is 0. Now as we approach that point from the left, our value of the function gets closer and closer to 1. Now what about if we follow or if we trace this? That means we are considering that values of x which are closer to 0. Okay, so we can clearly see that it is also approaching to 1 as the value of x approaches 0. That confirms our answer a while ago using the tabular method. Now what if we have this expression? Now we know that e raised to x minus 1 all over x is equal to 1. So we have to strategize in such a way we can extract that expression. So let's see if we will have the limit of 2e raised to x minus 2 all over x as x approaches to 0. Now as you can see, there is a common factor in the numerator. So let's factor that out. 2e raised to x minus 2 can be factored. So we extract the greatest common factor, that is 2. So we will have e raised to x minus 1. Now copy our denominator. As you can see, by applying the limit laws of the limit of a product, or the limit of a product and a constant and a function, you will have 2 times the limit of e raised to x minus 1 all over x as x approaches to 0. Now take note that this expression is just equal to 1. So it means 2 times 1, then we have 2. Did you get that? I hope you would be able to simplify expressions in the succeeding examples. Okay, now that is for the algebraic solution. Now what if we have the graphical method? So we have approaches 0. Here is 0. The ordinate of the point is 2. Now let's see. As the limit of the given function approaches to 0, okay, then we have arrived at f of x equals 2. Now let's choose another arrow from the left. Notice that it is also approaching to 0. So that confirms our answer that the limit of 2e raised to x power minus 2 all over x as x approaches to 0 is 2. Now let's have the limit of the logarithm of x to the base 6. So as x approaches to positive infinity. Now it's easier to use graph in determining the limits or in evaluating these limits. Now consider that the value of x increases without bound. So here is the tracing. Will there be a time that it will stop? Okay, there's none. So that means that the value of f of x increases without bound. So the answer is positive infinity. So take a look at that. we have positive infinity. Now, using tabular method, let's see, as the value of x approaches to positive infinity, or as the value of x increases without bound, we can have f of x is equal to this. We can notice that it is on an increasing trend. So therefore, we can say that the limit of the logarithm of x to the base 6 as x approaches to positive infinity is also positive infinity. Okay, now let's have a second example under the logarithm or the limit of a logarithmic function. So again, it's easier to graph. This is the graph of the function logarithm of x to the base 1/2. Now, as x approaches to positive infinity, what can we notice? The value of f of x is decreasing without bound. So therefore, we will have negative infinity. So let's use a table. So as you can see, the trend here of the value of x, as the value of x increases, then the value of f of x decreases. So therefore, we can say that the answer to this is negative infinity. Okay, now let's have the Euler number again. So here we have to plot the graph, or you can have tabular method. So as the value of x approaches to 0 from the right, it's like you will choose a big number to smaller until we reach 0, or a number that is closer to 0. And here is the corresponding value for the function. So here, what we can notice that it is decreasing. Okay, so it's decreasing without bound, so we will have negative infinity. Now let's take a look at its graph. Is it really equal to negative infinity? So as the value of the given function, okay, as the value approaches to 0, take note that the graph also decreases without bound, so it confirms our answer, that is negative infinity. So here are some key points for the limit of logarithmic functions. So take note, in number 1 and number 4 condition, b is greater than 0. And then we have the possible results. Okay, if we have x approaches to positive infinity, then it's positive infinity. Now, if we have the limit as x approaches to 0 from the right, then it's equal to negative infinity. Whereas if we have a fractional number for x, we will have the following: as the value of x approaches to negative infinity, then that is equal to negative infinity. The same with rule number 5. This is for values of b which is less than 1 but greater than 0. And for the third and the sixth, we have the limit of the natural logarithm. So take note, if we have the limit of ln x as x approaches to positive infinity, then it's equal to positive infinity. Now, if we have the limit of ln x as x approaches to 0 from the right, we will have negative infinity. Now let's take a look at trigonometric functions. So let's consider example number 11. Find the limit of sine x as x approaches to 0. So we can just evaluate this by replacing x by 0. So we will have sine 0 that is equal to 0. So therefore, the limit of sine x as x approaches to 0 is 0. Now let's confirm our answer using tabular method. So as x approaches to 0 from the left, we will have these values. Now take a look at the values. Let's study the trend. Now as the value of x approaches to 0 from the left, the value of f of x gets closer and closer to 0. So in other words, the limit of sine x as x approaches to 0 from the left is 0. Now let's have the other table. Now what if we choose values which are at the right of 0? Then we will have the following numbers: 1, 0.5, 0.2, and so on. Now, if we will have the corresponding values of f of x, we can see the trend that the value of f of x gets closer and closer to 0. So, the limit of sine x as x approaches to 0 from the right is 0. Now let's confirm using the graph of sine x. Now, looking at this graph, as the value of x approaches to 0, here is 0, which is the origin. As the value of x approaches to 0, then it's equal to 0. Now, from the right, we choose this. We can also see that the value of sine x gets closer and closer to 0 as the value of x approaches 0. Now let's take a look at the next example. Find the limit of cosine x as x approaches to pi n plus pi over 2, where n is an element of the set of integers. So with this, we can just evaluate using the concept of f of a. Okay, however, we can make it, or we can use graphical method to make it a lot easier. Now let's plot the points having the multiples of pi over 2. So as you notice, the ordinates of these points are all equal to 0. Therefore, the limit of cosine x as x approaches to pi n plus pi over 2, where n is an element of the set of integers, it is equal to 0. Let's have example number 13. Find the limit of sine x over x as x approaches to 0. We use tabular method. We select numbers which are at the left of 0. Then we would be able to have the corresponding value for f of x. So as we study the trend, as x approaches to 0 from the left, the value of f of x gets closer and closer to 1. So in this case, we can see that the limit of sine x over x as x approaches to 0 from the left is 1. Now let's take a look at the second table. This time we choose the numbers at the right of 0. And here are the corresponding values of f of x. And as the value of x approaches to 0, the value of f of x is equal to 1. So we can say that the limit of sine x all over x as x approaches to 0 from the right is 1. Now since they are equal, then we conclude that the limit of sine x over x as x approaches to 0 is equal to 1. Now let's confirm using the graph of sine x over x. So if we trace this here, we have 1. Now what if we have here the numbers at the right of 0, okay, approaching to that point? Both limits are approaching to 1, so therefore the limit of sine x over x as x approaches to 1 is 1. Now what about the limit of 1 minus cosine x all over x as x approaches to 0? So we now use a tabular method since substituting 0 to x will give us an indeterminate form. Now here's the trend of the x and f of x. So as the value of x gets closer and closer to 0, the value of f of x also becomes 0, almost 0. So we can say that the limit 0. Okay, now let's take a look. So here is the limit of 1 minus cosine x as x approaches to 0 from the left is 0. Now what if we choose the values at the right of 0? Now as we can conclude that as the value of x approaches to 0, the value of f of x is equal to 0. So we can say that the limit of 1 minus cosine x over x as x approaches to 0 from the right, we will have 0. Now since they are equal, we can say that the limit of 1 minus cosine x all over x as x approaches to 0 is really equal to 0. Now looking at the graph, we trace as we get to 0. Okay, here's that. Then as we approach to 0, as the value of x approaches to 0 from the right, we still have 0. So what if we are given sine 2x over x as x approaches to 0? Now if we evaluate this limit immediately at x equals 0, we will have an indeterminate form. So this can be 0 over 0. So in that case, we cannot simply substitute 0 to the variable since we will have an indeterminate form. So, but we know that sine x over x, is possible. So if we will have sine 2x, then I'll just write it as 2 times sine x. Okay, all over x as x approaches to 0. Okay, since we have a constant, we will have 2 times the limit of sine x over x as x approaches to 0. We know that this expression is equal to 1. So we can just say that it's equal to 2. Okay, the limit of sine 2x all over x as x approaches to 0 is 2. We can confirm that through its graph. If we will trace all the points from the left, we will have this, while if we have from the right, we will have this, and they both reach at 0, 2. Let me give you some key points in evaluating the limits of transcendental functions. Remember that we can evaluate limits of exponential, logarithmic, and trigonometric functions by using graphical method and tabular methods, especially when, after substituting the value of x, we have arrived at any of the indeterminate forms. Okay. Also remember that the limit of e raised to the x power minus 1 all over x as x approaches to 0 is 1, and the limit of sine x over x as x approaches to 0 is also 1, whereas the limit of 1 minus cosine x over x as x approaches to 0 is 0. Okay, so I hope you were able to absorb all the concepts that we have discussed in this lesson. See you again.